Welcome back. In this video, we're going to do example 5.5.2, where we're asked to graph the circles C1, which is r is 3 halves, and C2, r is 3 cos theta. Then we're asked to find the area of the region that's outside C1 and inside C2. So let's start by getting a handle on what this region looks like. So if I take circles, I'm going to take two circles and graph them side by side here. I know that my r is equal to 3 halves is a circle centered at the origin with radius 3 halves. And so if I put my origin there, then I know this is the radius of 3 halves. And I know that this circle C2 is of the form r is 2a cos theta, and its center, we remember from a previous video, is a, and so if a is, or if 2a is 3, then a is 3 over 2, which puts its center right there. And so its radius is also 3 over 2, which makes it exactly the circle that I have drawn. So we want the area that is outside C1 but inside C2, right? So this is circle C1, this is circle C2, which means that we're looking for this area here. And so we are going to use a double integral. If we call this region D, we have to remember that the area of D can be calculated as the double integral over D of 1 dA. And so we're going to describe our region D in terms of polar coordinates, because with a circle that's probably easiest to do. And then as I rewrite this integral as an iterated integral and evaluate it. So to describe this as a iterated integral, as this region D, we need to find values of theta so that our theta covers the region. So to find those values, we're not given them. We had better find the points of intersection of those two curves. And so we're going to let r1 equal r2, which means that 3 halves has to equal 3 cos theta, or cos theta equals 1 half. Now there's many different ways to solve that equation. I want theta, first of all, I want the thetas to go in increasing order, and I want them to be consecutive, increasing because this is the positive direction. I don't want to take my thetas in the opposite direction. I don't want to go around the circle this way because that doesn't capture D. I don't want to go around this way. I want to go exactly around the right part of the circle to capture D, and I want to go in the positive direction because I want my area to be positive. If I went around this way, I would have a negative area for D. And yeah, I could adjust, but why do that? Why not get it right from the beginning? So we want two consecutive increasing values that satisfy this equation. So there's different choices there even still, but I'm going to take theta is equal to minus pi over 3 and pi over 3. So theta is minus pi over 3 is this value down here, minus pi over 3, and pi over 3 is this value up here. So right away we have that our region, the inequalities in terms of theta for our region D are minus pi over 3 is less than or equal to theta is less than or equal to pi over 3. And then we need to look at the radius. We want radial values that are going to go through the region D from one circle to the other. And so we want to have 3 over 2, which is our smaller inner radius, less than r, less than 3 cos theta. So there's our region D described in terms of inequalities of r and theta. And so we are going to set up our integral now as an iterated integral in polar coordinates. So the area of D, well, that's the double integral over D of 1 dA, which is the double integral. So from minus pi over 3 to pi over 3 of the integral from 3 halves to 3 cos theta. Move this down a little bit, give myself a little bit more room. And 1 dA becomes r dr d theta. And so there's the integral that we need to evaluate. So let's start by doing that. We see right away that we have a theta in the bounds, and so we cannot factor this like we did in one of the previous examples. We have to go in order, and so we do the antiderivative of r, or an antiderivative of r, if I'm speaking carefully, which is 1/2 r squared from 3/2 to 3 cos theta. And we're going to run that in an integral from minus pi/3 to pi/3 d theta, which here is going to give me, so I'm going to have 3 halves, 9 halves, cos squared theta minus, and then what do we get? 9 quarters times 2 minus 9/8. And this will be from minus pi/3 to pi/3 d theta. Now cos squared theta, you may remember to evaluate that, there's some tricks, including one which is the half angle identity. So we're going to replace the cos squared theta by 1 plus cos theta over 2. So I've got 9 halves times 1 plus cos of 2 theta over 2 minus 9/8. Let's take our formula and clean it up here a little bit, which is going to give us, so the integral from minus pi/3 to pi/3. If I multiply this to, I'm going to get 9 quarters as my constant term, 9 quarters minus 9/8. So 9 quarters minus 9/8, that's going to give me 9/8, positive 9/8. So I'm going to get 9/8 plus, and then I'll multiply through 9 quarters of cos 2 theta d theta, and now we can anti-differentiate easily. So we're going to have 9/8 theta plus, and then the antiderivative that we're looking for is sine 2 theta over 2. So that's going to give me 9/8 there as well. And this will go from minus pi/3 to pi/3. So we are going to have, let's factor out a 9/8. 9/8, and we'll have, let's do the first here. So pi/3 minus pi/3, if I do the fundamental theorem with the theta first, and then the 9/8 I factored out, so I'm going to have sine of 2 pi/3 minus sine of minus 2 pi/3, so sine of minus 2 pi/3. This is going to give me, so 9/8 minus minus, so 2 pi/3. And then here, I'm going to use the fact that sine is an odd function, so this minus can come outside. Minus minus will turn that into a plus, so that'll be plus 2 sine of 2 pi/3, and then we're almost done. 9/8 2 pi/3 plus sine of 2 pi/3 is root 3 over 2. The 2's in the denominator will cancel with there, so 2 pi/3 plus root 3, and that is area, so that is units squared.